So today we have an excellent speaker lined up for us, Tanmay Gupta. So Tanmay is currently a research scientist at Prior with the computer vision team there. And this is over at the Allen Institute for AI in Seattle. So not too long ago, Tanmay received his PhD from UIUC, where he was advised by Professor Derek Hoem, and also collaborated closely with Professor Alex Schwing. And even earlier, he did his undergrad at IIT Kanpur in electrical engineering. In personal capacity, I've known Tanmay as a very friendly colleague and very sort of a generous, kind, and a helpful person, who was also generous and kind enough to leave some of the non-vision and language problem open for us younger researchers, which allowed us to graduate. His own work, of course, focuses more on the vision and language side of things, but lately he's also been delving a little bit into the embodied AI and spaces like that. But of course, today we are most excited to hear from him about visual programming, which is which recently won the Best Paper Award at CVPR this year. So over to you, Tanmay. The floor is yours.
All right. Thank you so much for inviting me here, Moitre, and also for the kind words. All right, so let's get started. So in the abstract, I promised I would talk about visual programming, and I would do that. But at the same time, I also wanted to use this talk to provide some context for general purpose vision systems and how our research on general purpose vision systems has led us to visual programming. All right, so just to get some nomenclature out of the way, what do we mean by general purpose systems? They basically are systems which are built once and then they're reused for various purposes, as opposed to systems that are designed specifically for one task, and then you discard that and start from scratch whenever you want to do a different task. So one of the key characteristics of these systems is, instead of having to learn these separate functions for different tasks like classification or captioning or segmentation, prediction, or whatever have you, we would like to have a single system that takes the input, in this case an image, and an instruction, and the instruction is what determines the behavior of the system. So if the instruction is to classify this dog breed, then the function f predicts a class label. If the instruction is to segment the cars, roads, and traffic signs, then the function produces segmentation masks for these things, and so on. And usually this is often referred to as instruction following system. So a few years ago, this work was actually started in 2020. And back then we still had to introduce kind of the idea of general purpose systems. But now that we have ChatGPT, we can just point to it, which is a great general purpose NLP system. And we all know that there are multiple ways in which you can prompt it to get your end task achieved. So you might describe the end task, like here I'm describing the POS tagging and defining the output format. And then given a sentence, the system has no problem just producing the POS tags in the desired format. Another way that people use the systems is in context learning, where I don't really have to tell it what I want from it. Instead, I just give it examples of input-output pairs. And then given a new example, it just treats it as a sequence completion task and produces the desired label. But these general purpose systems have been in the making for quite some time now. And a lot of it could be traced back to early vision language systems. So around 2014, 15, we started having these specialized systems that could produce captions or answer questions about images. And these architectures were very specialized to that particular task. The training data was very specialized to the particular task. And then gradually people started figuring out what is it that can be shared in the system across different tasks. So this is my own work from 2017, where we showed that you can learn image and word representations in a way such that they are not only aligned to each other, but they're also shared across tasks. So for example, whether you're doing object and attribute prediction or visual question answering, they would all use the same set of shared embeddings. And by doing that, you get some transfer across these tasks. So learning visual recognition helps you learn these embeddings, which improves performance on the VQA task and vice versa. Then around 2019, as transformers became popular, people started figuring out pre-training and fine-tuning strategies. So the early days of that was you would do cross-modal pre-training, very similar to how you would do mass language modeling in BERT, but now on image captioning data. And then doing that at scale made the system very efficient at learning new tasks. So then if you fine-tuned it for a VQA task, you would get pretty good performance very quickly. But at the same time, this was still a task-specific system in the sense that for every single task, you would have to fine-tune the pre-trained checkpoint on that particular task data. So a natural follow-up to that was multitask fine-tuning. So why not just fine-tune jointly on different tasks? And these tasks were things like image text matching or VQA. But the early attempts required you to have task-specific heads. So if you had an image text matching task, you would have one head which would have a binary prediction, a prediction over two classes. Whereas if you had a VQA task, you would have a distribution over the answer vocabulary. And both of these heads had to stick around and to be trained jointly. In fact, often if you had two different visual question answering tasks or two different visual question answering data sets, you would have two separate heads for these two. So when I began at AI2, one of the things that I was interested in thinking about was how do we make these vision language systems more general purpose? And we came up with GPV1. So GPV1 is this architecture which takes an image as input and an instruction and produces two kinds of outputs. For every input, it produces a text, which could be a class label or a caption, and it produces bounding boxes with the relevant scores. So, for example, if the query is what color is the dog, the output text would be brown, but at the same time, a bounding box is produced. And as you can see, it correctly localizes the dog. If you say, are there trees being seen? Then the output is yes. And then the bounding box head produces detection for the tree in the background. If you say, locate the dog, then you do get the bounding box for the dog, but at the same time produces some text, even though at training time, the localization task did not have any supervision for text. And so on for captioning and classification. Now, one of the interesting features of this architecture is that it does not have any task-specific branches. So what does that mean? Let's quickly look at the architecture. So there are two different input encoders. There's a visual encoder for the image, and we don't need to worry about the details about how it's implemented, but you can think of it as any visual encoder. And the language input is encoded using a language encoder. So the language input here is the task instruction. Now, both of these encodings or embeddings are fed into this cross-modal fusion layer, very similar to Wilbert. And then there are two output heads. There's an output head for language. So any task that requires producing captions, VQA, anything to do with text would use this language output head for producing that output. And tasks like localization and referring expression, which require producing bounding boxes with scores, would use this bounding box head. And so that is what we mean by modality-specific branches. Note that these branches are not task-specific in that we don't have a separate language output head for captioning and a separate language output head for VQA, but rather we have a shared head for one particular modality. And that's interesting because it helps do something that we call skill concept generalization. So what do we mean by skill concept generalization? Think of skills as these tasks like VQA and localization, and concepts as nouns, attributes, or verbs like cats and dogs. And skill concept generalization basically asks the question that if you have supervision for some of these pairs of skills and concepts, so for example, you have training data for VQA on dog images, and you have localization data on cat images, then can the model that is jointly trained on these two generalize to the other two combinations? That is, can you do VQA for cats and localization for dogs? And having this multitask model be trained with unified output heads is one of the things that helps us do the skill concept generalization. And we can measure that performance by holding out certain skill concept combinations during training and then evaluating specifically on those combinations at evaluation time. We won't go into details of these numbers here, but basically what this shows is we do get some benefit from jointly training with a unified output head, but there's still a long way to go. So for example, the classification number, as you can see, for specialized models that are trained on single task, and even for GPV1 architecture that is trained on single task, the classification output on these unseen skill concept combinations is 0. Multitask GPV gets some non-zero performance, but still abysmally low. So we did a follow-up work of GPV1. GPV1, even though it was able to perform these multiple skills, particularly 4 skills, and it was trained on COCO data, so it could understand 80 concepts and perform these skills on those 80 concepts, it was still limited. So one thing that we were interested in was how do we expand the concept vocabulary to 10,000 concepts? And so the way to do that was to disentangle the learning of skills from the learning of concepts. So instead of training this GPV1 only on COCO data and learning skills and concepts from that same data, we wanted to learn skills from COCO, but then learn concepts from web supervision. Now, this web supervision data is basically going to an image search engine like Bing or Google, and then searching for images for these 10,000 concepts that we are interested in. And then you could treat it as just any other classification data and jointly train the system on the COCO data for these 4 scales, along with classification data for these 10,000 concepts that we got from web. And the key thing that helps with learning these skills for these concepts is the skill concept transfer property that we talked about earlier. So here are some qualitative results to show that. There are 5 tasks, and for each task, the green output shows the prediction of the model that was trained with web supervision, and the red shows the prediction without web supervision. So in VQA, you can see the question is, what is the type of dress the woman is wearing? And with web supervision, the model says sari, which is the correct answer. Whereas without web, having been trained only on COCO, it has no idea what sari is. So it just says scarves. Similarly, for the classification, you say, what is this thing? And it's a gondola. But then if it was just trained on COCO, it would have no idea what a gondola is. And to drive that point home, we further tested it on images and concepts that we knew did not exist in any data set before 2020. So COVID images. So basically for concepts that are related to COVID, like COVID vaccination card or KN95 mask, we went and collected a handful of images and fine-tuned the system on that. And you can see that even though that data was purely classification data, it did not have any questions or answers or captions. The model is still able to perform the same skills of VQA captioning and localization and so on, but with these new concepts. So we basically answered this question: how do we make vision and language systems more general purpose by proposing to have modality-specific heads and doing away with task-specific heads. And this today has kind of become the norm, as most people just use a language decoder for anything that's related to language. And some people have also tried doing similar approaches for bounding boxes. My colleagues at AI2 have also pushed this further with a system called Unified IO, where the hypothesis was, what if we tokenize the inputs and outputs into some token space? Then would all the tasks that we're interested in, whether it is segmentation or surface normal prediction, just convert into sequence-to-sequence translation problems? And that question was also answered in the affirmative. It's a system that simply predicts sequence of tokens from sequence of tokens, And any task in computer vision or NLP can easily be formulated into that, as long as you have these tokenizers for the kind of output that you're looking for. And I believe the tokenizer that was used here was VQVA. So if you have a segmentation mask, you would just feed the segmentation mask as an image into the VQVA and get tokens for it, for example. So as we were building these general purpose vision systems, there was another important question, which is how do we evaluate these general purpose systems? And it's not sufficient to just evaluate these on separate data sets and benchmarks, but you also have to worry about evaluating these diverse visual capabilities and focusing on how well the system generalizes to novel concepts and novel data distributions, and how well the model is calibrated and how robust it is to various kinds of noise in the image. So we created this grid benchmark for doing this. And one of the interesting properties of this benchmark is for every model that you submit, which is capable of performing these 7 different tasks that we have in the benchmark, you get up to 500 metrics that would inform you about your model. And these are metrics that have to do with generalization, robustness, and calibration. So this was the path that we were taking to for a long time. And clearly this path leads to more data and more compute and more parameters, basically the same route that LLMs have gone over the past 5 years. But we found ourselves questioning if there's a better way of doing it, a way that requires little to no new data, little to no new learning, and something that can use existing models. And around the same time, LLMs were getting really, really good at generating code. And so that is how visual programming came into being. It's a very simple idea. You generate code using an LLM, and then that code is executed on your inputs to produce a desired output. So here's one particular example, and then let us see how we would solve this example or this particular task if we were doing it ourselves instead of an end-to-end system. So we want to tag the characters on the TV show Big Bang Theory. We would probably begin by detecting faces. Then we would either from memory or querying a knowledge base come up with the list of characters that appear on this TV show. And then somehow using memory or using some system, we would match these faces to the names, and then we will visualize the output for the end user. Now, imagine what it would take to build an end-to-end system that does this. So a system like Unified I/O, if you were to get into this task, it would have to learn skills like face detection, knowledge retrieval, image text matching, image processing, and plotting the final result. And that is only for one single task. Now, imagine if you had to do thousands of such tasks, you would quickly need a much larger training funnel to funnel in all of those skills into this parameter space of the end-to-end model. And that quickly becomes difficult. But at the same time, if I gave you existing models for detecting faces and retrieving character names from a knowledge base or matching faces and names, then all of you, I'm sure, can write a very simple program that would be able to solve this task. So you would have an implementation for each of these steps for detection and matching and so on. And then there's a part of the program which invokes these steps in some logical order. And then that program is executed on the design input to get the output. And so that basically shows us that you can replace this end-to-end training paradigm with a program invocation paradigm where these skills are available to you as functions and you just invoke them in a program. And that is what visual programming is about. So you begin with a natural language description of a task, and then use a program generator to generate a program that's then executed on the task inputs using a program interpreter to get the output. So it's a general framework, and then the specific implementation of it is what we call VisProg, where we use in-context learning in LLMs to generate the programs, and in Python with a little bit of HTML for visualization to produce outputs. So the core components of WisProg are its modules. We have modules for image understanding, image manipulation, knowledge retrieval, and arithmetic and logical reasoning. So for example, we have stable diffusion for replacing pieces of the image. We have VQA for answering questions about image, and so on. So these WisProg modules essentially can be anything ranging from neural models to image processing libraries to any arbitrary program that you have in mind. So now let's look at what these programs themselves look like. So here's the instruction: replace the desert with lush green grass, and we have the image. And at the bottom is the kind of program that our WisProg system generates. So you will notice that it has multiple steps. In each step, we invoke a particular WisProg module. These modules have as input various arguments. You can have one argument or more. Some of these arguments are Python primitives like strings or integers or float and so on, whereas others are arbitrary Python objects that are produced in previous steps. So these could be a list of segmentation masks or detections or whatever you can come up with. And then executing this program produces the final result, which is this particular image with the desert replaced by grass. So how do we generate these programs? We somehow have to provide a language model with information about what are the kinds of programs that you would like to generate and what are the tools that are available for the task. And then that information has to be concatenated with the instruction for which you want to generate the program. And again, there are multiple ways of doing it. One particular way is in-context learning, which is what we use in the visual programming paper. So you give it in-context examples of instructions and desired programs. And through that, GPT-3 is able to figure out what are the tools that are available. So for example, here we have face detection, selection, emoji generation models available. And then it knows how to invoke these programs or how to invoke these functions in context of the program. So it knows what are the functions and what are their argument structures and what are the types of inputs that can be fed into each argument in the function. So given this, GPT-3 is now able to generalize to new instructions and produce similar programs. And executing these programs can produce not only the output, but also a very interpretable execution trace, which is something that end-to-end models have been lacking for some time. Like, we don't really know how to debug the prediction of an end-to-end model. But for visual programming, that is not an issue at all, because you can just step through the program and see what exactly is the output. So here we have the query: tag these famous computer vision researchers from Berkeley and Stanford. And this is the program that's produced. So as you can see, it produces Jitendra Malik and Fei-Fei Li and produces bounding boxes for them. You can also do face replacements. You can say replace Jitendra with George Clooney wearing sunglasses and Fei-Fei with Aishwarya Rai wearing sunglasses, who is an Indian actress. And it has no problem doing it using a combination of face detection, selection using clip, replacing using stable diffusion, and then doing that again for the other person. And here's the visual rationale that I was talking about. So this is the generated program, and then we are stepping through the execution trace of that program. So you can see exactly what happens in every step. So that was basically all of visual programming. But WisProg really just scratched the surface, and there are a lot of challenges in using it in consumer applications, and also to make it more robust. So the first is in visual programming, we generate a program and we execute it, and then if it fails for any reason, we don't really do anything to fix it. Whereas ideally, we would like to be able to identify the causes of errors and then self-correct. Some of those errors are because of syntax of the program that's generated. And that is kind of easy to fix as well, because you can just run that program, get your error messages from the terminal and plug it back into a language model. And to some degree, it will fix those errors. What is more difficult to fix, and often the cause of errors in systems like WISP-PROG today, are the errors in predictions of models. So let's say at some ith step in the program, you're asking a detection model to detect dogs, and then the model does not produce the right detection. So it produces detections for some other animal, or produces some false positives or false negatives. That could completely mislead the execution of the rest of the program. And one thing that's required to fix that is confidence scores. So we don't really have well-calibrated models with confidence scores that we can trust. So it's difficult to make a judgment about whether the prediction is right or not. What we also need, and there are some papers that are doing this now, is multi-step program generation. So instead of generating the entire program in a single shot, we would like to generate pieces of the program, run that particular piece of the program to get some output, and then determine what is the next steps in the program based on that output. Systems like ChatGPT make it quite easy to do that, because you can have this conversation kind of a prompt that generates these programs and executes them in pieces. And with GPT vision coming out, maybe some of you already have access to it, you can also do multimodal program generation. So instead of just generating a program based on the language description, you can generate programs given the input image as well. And sometimes that can be helpful, because just given a language description, the program can be ambiguous if you don't really see the image. Another thing that we would like to get to at some point is have this WISP-PROG generalized to thousands, if not hundreds of thousands of tasks. And the challenge there is, how do you incorporate these different capabilities that are spread across various models on Hugging Face, or various libraries in Pip or whatever library manager you use, and then how do you build a system that does not require a user to specify these in-context examples, because that is one of the pain points of WISP-PROG currently. Now, often, when people ask me, like, what is it that excited me about WISP-PROG, it was the image editing capabilities. So things that we thought we needed diffusion models trained to do, like replacing people's faces and whatnot, and all of that required having one model that is able to detect people or detect objects, segment, and then do the replacement. We are now able to just invoke them in sequence, and they can be different models. You can use the state-of-the-art object detector, you can use state-of-the-art segmenter, and then you can use state-of-the-art image editing models together to get the desired output. But extending it to video models, or like video editing task, is a challenge, because then you somehow need to still figure out how to ensure consistency across frames. And the last part, which I don't really have a good answer for, is how do we get WISP-PROG to learn based on its interactions with users. So today, WISP-PROG is a fixed system. You have in-context examples that maybe you can do something to update them over time, but then the modules themselves are frozen. The program generation capabilities are kind of frozen with whatever is available with the LLM. So how do you get learning involved in that process? So if I spend a day with WISP-PROG interacting with the system and providing feedback, how do I get WISP-PROG to improve over time? And there's obviously work in RLHF for improving language models using human feedback. Maybe some of that is applicable, but it still is a problem applying that to a system like WISP-PROG, because you need to kind of identify at what step is there a failure, especially for model prediction failures. So I guess that was the last slide that I had, and I'm happy to take any questions.